So now we're going to take a look specifically at activation energy and eventually the Arrhenius equation, which relates to activation energy. So we had talked about what activation energy is. It's the amount of energy required to get reactants to go to products. So in order for reactants to actually combine together or break apart, whatever it is, and form products, they have to get at least this amount of energy to get them over that hump and form the products. If they don't receive at least this much energy, that energy to overcome that hump, the activation energy, reactants will never turn into products. And the way they can get that energy is from collision, so you heat up the reaction, they collide faster, and that collision, the energy from the collision has to be greater than the energy of activation in order to form the products. So activation energy in terms of exothermic and endothermic reactions, we've learned what those are. Exothermic reactions are ones that release energy to the surroundings. Endothermic reactions are ones that absorb energy from the surroundings. So if you look at the energy of the reactants versus the energy of the products, and it's shown right here on the histogram, so the reactants in this case have higher energy than the products. So what's going to happen then is the reactants will receive their activation energy from their collision, and then they'll turn into products. And when they do, they actually lose some energy too. So they started with a certain amount of energy, got their activation energy, spit back out their activation energy. So think of this like a ball being thrown up and then falling back down. So not only does it get the activation energy, then release that activation energy back to the system, but it also releases some of its energy that was built into the bonds beforehand. And that difference right there, that amount of energy is the difference between the reactants and the products. That is the energy that's released to the system. So it received the activation energy, gave back that activation energy, so potential energy, kinetic energy, and then not only that, but lost a little bit of energy, and that's the release, and that's what makes this exothermic. An endothermic reaction, on the other hand, we take a look at the reactants versus the products. So the reactants have a lower energy than the products do. That means the reactants need to gain this much activation energy to get them up over the hump, but then when they turn back into products, they hang on to some of that energy in their bonds. So not all of the activation energy is re-released. Okay, some of that activation energy is hung on to and kept to keep those bonds going. So that energy then, in order for those bonds to stay, is the energy that's absorbed. And that's what makes this an endothermic reaction, because it absorbs some energy, and that energy on top of the activation energy is what gets this guy going. So their collisions aren't going to be enough. It needs to get other energy pulled into it as well. So what you can also see from these two diagrams is why it is that exothermic reactions proceed a lot better with less input from the system. And it's because this energy that's released in an exothermic reaction, that energy that's released, it's not just spit off into nowhere. That energy can be turned around and used as activation energy. That's why when you light something like a Bunsen burner, you just give it a spark once. Okay, and that spark gives it the activation energy to trigger the reaction. But once you trigger it, it's going to produce energy, it's going to release energy, and that released energy can be used as activation energy for other reactants, and it can complete its own cycle. So this reaction is self-sustaining in a way. It creates its own energy to get over that activation hump, as opposed to an endothermic reaction. So an endothermic reaction, you have to put in energy to get it over its activation energy, but then once it goes, it keeps some of that energy. So you have to keep supplying it with energy in order to keep it going. So a reaction like this would be one that you have to keep on a hot plate. You'd have to keep it heated up. You have to keep putting new energy in order to keep it going. If you stop that energy flow, the reaction itself will stop as well. Whereas an exothermic reaction, you just give it the energy once, trigger it, and it keeps going. Let's look at the activation energy for a reversible reaction, so reaction at equilibrium. Taking a look here at AB plus C, which is yielding A plus BC. We saw that one a little bit before, but now it is at equilibrium. So that means not only are A and B reacting to produce C, but A plus BC is also reacting to produce these guys again. And so we end up with that dynamic equilibrium, that cycle, where the concentrations end up just staying the same, but they're constantly going back and forth. So the forward reaction of AB plus C, it's got that hump, and then it has the products over here. And then if we just write the reversed version, so we're just taking this and putting it on the product side as opposed to the reactants, we can see it's basically the same diagram, just flipped. Okay, a mirror image of these two, where now the products have to overcome the activation energy, and they keep some of that energy. So on this side, you should be able to look at this picture and say, all right, so reactants start with more energy than products. That means it is going to release that extra energy to the system. And over on the other side, we can look at this and say, all right, products have less energy than reactants. That means it's going to require some energy absorbed from the system. So that means this side is going to be an exothermic reaction, and this side will be an endothermic reaction. So what that means is the forward reaction in this case is probably going to be favored, because you look at the forward reaction and its activation energy is lower. That means an AB plus C requires less energy than the A plus BC. So the forward reaction requires less energy than the reverse reaction. So if we were to talk about this in equilibrium terms, we would say that equilibrium for this would favor the products. So it's going to be more likely, these two are going to be more likely to react than these two. And we can also think of this in terms of Le Chatelier. So Le Chatelier says if you stress a system, it shifts. So if you start putting energy into this system, if you start heating this up, it's going to give it more activation energy, so you're going to be able to supply this reaction and drive this one back. Okay, so by supplying more energy to it, we can cause these to have a little bit more clout and drive our reaction back to the left. Alright, so it's a little bit of calculations with the Arrhenius equation. So Arrhenius should be a familiar name. He's the Arrhenius who told us about H pluses and acids and OH minuses for bases. Also brought us the Arrhenius equation, which we use to calculate activation energy based upon a rate constant. So if we know a rate constant for a particular reaction, we can find out what its activation energy is in the form of joules. So how many joules of energy are required to activate a reaction, to get it over that hump. So the reaction is the natural log of K, our rate constant, is equal to the negative of EA, that's the activation energy, divided by R. This R, since we're talking about joules and Kelvin for our energy, that means it's going to be the 8.314 joules per mole Kelvin, not the 0.0821 of the gas laws. Temperature, capital T, that means absolute temperature, which is Kelvin. And then A is a constant that's related to whatever reaction we're talking about. So that's something you would either have to calculate or something that would be given to you, and it depends upon the reaction. And that's going to be related to what kind of collisions are required for the reaction to proceed, whether they need to be hit really hard or they need to be hit with a certain angle, that kind of thing. So once again, let's use math to help us do a little bit of chemistry. So if we have our Arrhenius equation written just like this, what we can see then is y equals, what's that? mx plus b. And so in the case of the Arrhenius equation, our y value would be the natural log of K. Our slope would be the activation energy, the inverse of the negative of the activation energy divided by R. Our x value, so our x-axis, would be the inverse of the temperature. And our b, our y-intercept, would be that collision frequency. So if we wanted to graph this information, we would graph the natural log of the rate constant by 1 over the absolute temperature. And so keep in mind the rate constant, the K, is temperature dependent. So if you change the temperature, you change the K. So in order to figure out what the activation energy is for a particular reaction, scientists will do a very similar thing to the other data that we looked at. They'll vary one thing and see how it affects something else. So in the case of figuring out what the activation energy is, they would take a reaction and they would keep the concentrations all the same, but they would change the temperature. They would change the temperature, see what the new K is, and then plot those lines. Because if we get those different K values at the different temperatures and we write a plot for those, we'll end up getting a straight line. And then the slope of that line would give us our negative of the activation energy divided by the R. And since R is a constant, we can use that little fact right there to help us find the activation energy. So all you would do is just fluctuate the temperature, see what the K is at each of those temperatures, get maybe 5 points, use those points to find your slope. So here's an example graph to show that. So some scientists somewhere, they did some experiments where they changed the temperature and they found the K at those different temperatures, and then they plotted that data. So on their plot they got this straight line, and we can use that straight line to then find the activation energy for this particular reaction. So they got the natural log of the rate constants and then plotted them against the inverses of the temperatures, and then this is our slope. So let's go ahead and shrink this down. And we can use the slope to find the activation energy. And so since slope is just rise over run, let's find our slope as the rise, which would be the differences in the k's. So we're going to just use the plots that we find there. So it would be -5 minus -1. We're going to divide that by the run, which would be our inverse of temperature. And so we're going to use 3.8 times 10 to the -3rd minus 3.4 times 10 to the -3rd. And so that ends up getting us our slope, which is -1.0 times 10 to the 4th. Now let's talk about units here. So first off, the natural log of K. K has a variety of different units. It can be molarity, it can be molarity in seconds, it can be squared or 1, all kinds of different things. Temperature is Kelvin, absolute temperature, capital T, so it's going to be in Kelvin. Our K, notice how they don't give us units for that. It's because it's irrelevant. K deals with rates, and rates have nothing to do with our actual Arrhenius equation. So if you look at the Arrhenius equation, it deals with temperature, it deals with energy, but it doesn't really deal with a rate, with molarity at all. So units of K are irrelevant to the Arrhenius equation, so we don't need them. However, our units of K, we are going to need those because R has K in it, and so we're going to need to plug those in. So the units on these two guys down here at temperature, they're both K. And so that means the units of our slope is also K, Kelvin, for temperature. But the units of our top number of our rise, they don't matter. So then we use our slope in the Arrhenius equation. Okay, and we know that the slope is equal to the activation energy divided by R, and it would be a negative. So then we can take this equation and rearrange it. If slope equals EA over R, and it's a negative, then we could say that EA is equal to the negative of the slope times R. And so it would be the negative of -1.0 times 10 to the -4th K times R, which is 8.314 joules per mole Kelvin. And so what would our units be here then? Well, we've got Kelvin canceling out Kelvin, which means we're left with joules per mole. So let's figure that out, and we wind up getting 83,000 joules per mole, which is the same thing as saying 83 kilojoules per mole. So what that means to us is that it requires 83,000 joules of energy for every 1 mole of reactant in order to get over that activation energy hump. So just to get over that activation energy and form the products. So it's going to be that distance right there. So 83 kilojoules would be the activation energy, so just that amount of energy right there. If there's an exothermic reaction, it's going to generate energy, and that energy can in turn be used to drive the reaction. So the 83 kilojoules might be the only energy, you only have to give it to it once. So 83 kilojoules, that'll start the reaction. The exothermic, the energy produced, will continue to add that activation energy for further reactants. If it's an endothermic reaction, though, you're going to have to add that 83 kilojoules for every single mole of reactant inside of that vessel. So it's going to need that continuous supply of energy to get up over that hump, because it's going to be always taking in energy, never giving any back. So that's activation energy and how it plays a role in kinetics.